to know what to talk, because I wrote it like everything by myself. So today we're gonna explore the nature of particles and antiparticles. So we're gonna start with so how it all came around. So in 1928, a British theoretical physician called Paul Dirac, he has developed a theory that combines quantum mechanics and special theory of relativity proposed by Einstein. So just briefly, quantum mechanics is just a theory that describes the behavior of subatomic particles, and the theory of special relativity is just a theory that can describe the behavior of particles or something else that are traveling at speeds closer to the speed of light. And he actually managed to derive an equation which is now known as Dirac's equation. And then he found out that his equation actually gives multiple solutions. So for this example, we're going to use an electron. So an electron electron was a particle which satisfied the Dirac's equation, and the other particles that satisfied the Dirac's equation was like an electron with the same mass but with opposite sign charge. And 3 years later, after the 3 years, this was a time when he actually admitted that his equation actually predicts a brand new concept in physics, and which is now known as antiparticles. And so we need to realize that every particle, every subatomic particle, every particle, and we can also make elements, anti-elements. So it's important to realize that every antiparticle has its twin of the same mass but with opposite sign charge. For example, an electron will have an antiparticle which is called positron, exactly the same mass but with opposite sign charge. By going further, not only the charge is reversed, but all the internal quantum numbers, which are kind of, if you might think, is just predefined characteristic of a particle that it has due to its nature. And it's important to realize, so if we go back to the Big Bang and the early universe, so within a billionth of a second after a Big Bang, the average temperature of the universe kind of exceeded the value of 10 to the power of 26, I believe, Kelvin, which kind of implies the tremendous amount of energy that was concentrated in a very small region of space-time, which therefore has caused this energy to materialize. Remember that matter is just a very compact form of energy. So, and when the energy was materializing itself, so what actually happened is that particles, so all the matter produced, particles and antiparticles were produced in exactly equal amount. And we will actually explore the process called pair production to explore why we know that the initial distribution of particles to all antiparticles was exactly half. And now you might really ask yourself of why everything is made out of matter, and we can't really observe antimatter in our universe. And the answer to that question is, it is actually still unsolved. It is one of the biggest questions in particle physics that they're trying to answer. And now we're going to talk about Standard Model as a theory. So we're going to touch upon Standard Model as theory, and we're going to touch upon subatomic particles. And actually, this theory is kind of quite successful, but it can't really explain this question that I've just mentioned. So, okay, so let's start with subatomic particles. I'm going to briefly describe each particle and what it does. So all subatomic particles are divided. So they're divided into two main subgroups. We're not talking about families, hadrons and leptons. We're going to talk about subgroups. So they're divided upon a characteristic called spin. Okay, spin is a very hard concept to understand, because the definition of a spin is an intrinsic angular momentum. But as you might think, angular momentum is in classical view, angular momentum is how hard it is to start or stop something from spinning. But I don't want you to apply your classical analogies, nothing actually spinning, because, and this is why quantum physics is quite hard to understand, because classical analogies that we all have doesn't really apply to quantum physics. So spin is just the intrinsic property of a subatomic particle that it has due to its nature. nothing to do with spinning, nothing is actually spinning. So, and it is divided into two main subgroups, so it's fermions and bosons. Bosons are known as force carriers, and so divided into fermions. Fermions have a spin that is a multiple of a half, so where n equals half, 3/2, and etc. Bosons have a spin that is a multiple of an integer. Oh, sorry, this is reduced Planck's constant, sorry. This is what the spin is measured in, so where n is 0, 1, and etc. So we're going to start with fermions. So fermions, they have quarks and leptons. So quarks, so these are all subatomic particles, which means they don't have inner structure. So fermions, they have quarks and leptons. So we're just going to briefly describe what the quarks are. Quarks come up with 6 different flavors: up, down, charm, strange, top, and bottom. And scientists sometimes call this as a first generation, second generation, and third generation. Honestly, I don't know why they're calling this, and yeah, it's kind of confusing. And so this is quarks. We're going to go back to them. And now we're going to talk about, I'm just going to briefly write leptons. So we have electron, muon, and tau. And these are just heavier siblings of an electron. They behave exactly like an electron, but they have greater mass. And here we have, yeah, I can't draw that. So electron, something like that. Electron neutrino, muon neutrino, and tau neutrino. These guys are very small. Their mass is like millions of times slower than electrons. And actually, quick fact, neutrinos don't like to interact. And actually, it is a fact that if you send electron neutrino, it can fly through a lead, like metal lead, for 1 light year without interacting with anything, because it's neutral and it's very, very small. And so let's go back to the quarks and leptons. And a quick point to realize that actually up quark, down quark, and electron, they are basically the fundamental building blocks of our universe. So basically, you can make almost everything from these ones, because this is what actually proton. So proton has UUD, so up, down, and it has a net charge of +1. So yeah. And now you might really ask yourself, why do we need top and bottom charm, strange, muon, and tau? And yeah, it's kind of confusing because we only observed these in our particles accelerators for a very short period of time. And now you might think that there is no point on them, but however, they have been produced during the Big Bang, and if, as I said, within a billionth of a second, tremendous amount of energy has been materialized, and these particles were produced as well. But what actually happened? Within the next fraction of a second, these top and bottom charm, strange, and muon and tau, they were very unstable, and then they just died out within a fraction of a second, leaving loads of neutrinos and EM radiation that we can actually still observe as a relic radiation. And here I'm actually going to just say, so top prefers to decay to bottom, and bottom prefers to decay into charm, charm prefers to decay into strange, and strange prefers to decay into up. And here, but sometimes it kind of varies because charm quark can decay into a down quark, and down quark can decay into an up quark. So this is what actually happens. This is so charm, strange, top, and bottom. They were very unstable, so we are left with down quark and up quark. Down quark, they can decay into up quark, and up quark can decay into down quark. And we will explore the process called beta minus decay to actually see what's actually happening. Okay, okay, I think we're going to start talking about bosons. And, oh no, before that, I need to say about the discovery. So, also, quick fact, the way quarks were discovered is kind of similar to the way the structure of a nucleus was discovered. So basically what happened is scientist has fired a electrically charged particle which was accelerated through a large hadron collider into a neutron. And what actually happened, when they fired a very high-speed electron, what actually happened? It scattered from the neutron. And at this moment, scientists had realized that although neutron is overall neutral, it still has a magnetic moment, therefore saying that there is still charge within a neutron that counterbalances itself. Therefore, and some of the evidence that electrons were deflected by an angle larger than 90 degrees have proven that there was indeed a collision, a direct collision with charged particles with a constituent quark. So that's how quarks were discovered. Also, before we move on to bosons, it is actually it's quite interesting because the analogy that the motion of electrons determines the size of an atom. For example, this is an atom. Let's say we have an outer electron. This is quite abstract, but let's say we have an outer electron if n equals 2. So what we're saying, when this electron absorbs a photon that carries energy equals hf, if a photon carries a sufficient amount of energy required to jump to the next orbit of an electron, so it can excite an electron, now we can see that electron has a new orbit that has kind of larger distance. It's just an analogy. It's a larger distance from the nucleus. And now we're saying that atom actually, it has bigger size now because the size of atom is governed by the principle of where is that outer electron orbiting is. So yeah. And the same actually happens with quarks. So let's go back to the proton now. So it's UUD. So this neutron, this proton. So what actually happens? If we excite one of the quarks, and we will explore the concept of quark confinement. So if we actually directly hit one of the quarks, it will kind of elevate in energy state, and the distance between neighboring quarks will actually increase. And this is quite interesting fact to have, and we will go back to this to explain why we can't completely separate one of the constituent quarks and study it individually. Okay, so now we're moving on to bosons. Okay, so it's important to realize that when particles are interacting, what actually happens is particles exchange momentum, energy, and information. So, they exchange it in the form of a bosons and force carriers as elements. So, forces, elementary forces, gravity, strong nuclear force, weak nuclear force, and electromagnetism are all mediated by elementary subatomic particles called bosons. So we have gluon, photon, W boson, and Z boson. And here we have Higgs and speculation going on about graviton. I don't know how to, but we're not going to mention it. We're not going to mention it because so to have a better understanding of why are they known as force carriers, I'm actually going to show you an example of an electron interaction. So what actually happens if you fire one electron in this direction and one electron in that direction? So what's actually going to happen? As we all know, electron will follow kind of this trajectory, okay? And we all know that, and we say this is because light charges repel, okay? Yeah, that's kind of basic. So, but what actually happens? We can express this using Feynman diagrams. First, we need to label time, because it's quite important when you're using antiparticles because they have different directions. And so what actually happens? One of the electrons is following this trajectory, and one of the electrons is showing this trajectory. So before I explain that, we actually need to realize that an electron is not, by quantum field theory, electron is not some kind of it's not as you imagine it. It's not like a pinpoint ball that just exists. What actually is an electron? Electron is an excitation of electron field, and it is governed by quantum field theory, which says that all subatomic particles is just the excitation of their corresponding fields. So here, so if I can just picture it as a water. So if we have a field, let's say it's electron field, and if you in the water, so if you have a water surface, and if you just top your finger in it, you will kind of create some kind of a wave. So this is what actually happens. This is just an analogy. So when energy is present in one of the quantum fields, it causes an excitation, and this excitation is what is called is an electron. And the same happens with photon. Photon is just the excitation of electromagnetic field. And actually, quite interesting. It's not really a fact, but it's quite interesting idea. You know that from A-level physics, we know that the intensity is proportional to the amplitude squared, and intensity depends on energy. So we can actually kind of link a good understanding of energy being dependent on amplitude squared. So when we apply more and more energy, the excitation amplitude, so let's say this amplitude of excitation kind of increases, so this particle has greater energy. But this is just an example of what I was thinking. So, and here, so let's go back to this analogy. So we have electron and electron here. So what actually happens when they travel this direction, at this point when they repel each other, what actually happens? At this point, the excited region of electron field, let's say this, interacts with an excited region of electron field here. And at this point of space and time, what actually happens? One of the electrons emits a photon. So the photon is emitted by this electron, and photon is absorbed by this electron. And this is why, so photon, photon have zero mass. And but photons still have a momentum. And what actually happens here, this electron, so traveling in this direction, emits a photon that has a momentum. Therefore, to conserve the momentum, it has to travel in other direction to conserve it. Same happens with this electron. And now you can see how actually forces are mediated. And the next level of going to the Newton third law. So so this is what's just in my head, and I think it's kind of a good example. So when I actually push the wall pushes me back because the electrons in my hand exchanged billions of photons that carries momentum that will kind of, due to conservation of momentum, the wall not moving. So yes, and before we're moving on, how can we make antiparticles? I have explained only photons, and I'm actually going to explain quite briefly about everything here. So gluons are force carriers, and what are they doing? Gluons is like a glue, so they glue quarks. So, and have you ever asked yourself of why if a nucleus is made out of positive and neutral, so neutral and positive, why nucleus why is it still very compactly packed together? Because if we use logic, this would really just explode. And the reason for that is gluons. Gluons they mediate strong nuclear force. Strong nuclear force is acting in the nucleus and between the quarks that keeps quarks together. And this is, when I was reading just A-level, our A-level physics book, as they said that strong nuclear force, due to its strength, its very high, very large strength, we can't really separate the quarks. But this is not actually completely accurate, and we will explore again. We'll explore quark confinement. Beta, not beta, W boson. So W boson and Z boson is responsible for a decay process. So what actually happens? You did triple science. So in triple science, you've done a beta minus decay. So what actually happens in beta minus decay? An electron is emitted with antineutrino to conserve lepton number. But what actually happens if, let's say, we have a neutron, so DDU, and then we have to turn it into a proton. So in the process of beta minus decay, what actually happens is down quark stays the same. Up quark, this up quark just stays the same. And what actually happens with this down quark? A W minus boson is emitted. W minus boson is emitted, which then decays into an electron and antineutrino. Remember when I said antiparticles have reversed internal quantum numbers? In this case, electron has a lepton number of something. I don't know what is a lepton number, but so this is electron neutrino, and so this is a conservation of a lepton number. And the actual reason for why so the weak nuclear force was mediated by W minus boson. But very interesting fact here is actually W minus boson has a mass that is greater than the whole nucleus, and this idea is governed by Heisenberg's uncertainty principle for energy and time, and we will explore it later. Yeah, so this is what actually happens in a weak interactions. Okay, Higgs boson. This is what the mass of the whole of all particles is. This is the guy who is responsible for the mass of all particles. And if you think, so the question is why some particles have different masses, and if we go to quantum field theory, it just describes some particles have different masses because of the way they interact with Higgs field. So if you interact a lot with Higgs field, you will have a lot of mass. If you don't really interact with Higgs field like a photon, you will have no mass. Okay, we're moving on. How can we make antiparticles? Okay, so we make antiparticles in our colliders, for example, like Hadron Collider at CERN, Fermilab, and Stanford linear. There's loads of colliders. So, and what we're actually doing is we're taking charged particles like electrons and protons, and we are accelerating them using a very strong electric field. And so the charged particles reach very high speeds, like closer to speed of light. And actually, what actually happens as the velocity tends to c, the energy carried by the particle increases. Increases, but not like in a linear proportion. What actually happens is if we draw a gamma graph here, and this is percentage of speed of light, and this is 10, 20, 30, 40, 50, 70, 100. So what actually happens? At low speeds, gamma is not really increasing much, but starting from 70%, it starts to kind of significantly increase, and it tends to infinity as we tend to speed of light. So as we reach velocities closer to c, the energy is kind of growing exponentially that a photon or an electron carries. Note that the mass doesn't increase, but the energy does. And at this, so I'm just gonna explore the equation that actually just shows the collision of two protons. So what actually happens when we collide two protons? As a result, we're getting proton plus proton plus proton plus antiproton. And now you might really ask yourself, well, where these two guys came from? And the actual answer is the kinetic energy. So the kinetic energy of this has been converted into a particle and antiparticle pair. So the kinetic energy was materialized into particle-antiparticle pair. And important here to note that this will most likely come into a meson, which is just, we'll explore adequate confinement. And they will kind of annihilate. So this happens for a very, very short period of time when they actually here existing, but they will annihilate emitting radiation. We will explore that later. And actually, when I was doing that research, I tried to calculate the minimum speed required for individual protons in head-on collision. And the reason why I failed, so I failed calculating the speed, the reason for that is because I used good old kinetic energy, which is equal to half mv squared. So, yeah, this is quite a stupid thing to do because as we reach velocities closer to the speed of light, remember we have to use relativistic kinetic energy. So I ended up having velocities which is 400,000 meters per second, which is greater than the speed of light. Yeah, and actually, I'm just going to briefly show you how you can actually estimate the average, the roughly kinetic energy of an object which is traveling at relatively low speeds. So what you're actually doing, you have to realize that kinetic energy equals E total minus E rest. So an E total is defined by Einstein as gamma mc squared minus mc squared. So what actually happens here, you know that gamma is 1 over square root 1 minus v squared over c squared. And if you take mc squared, this, and 1 minus v squared over c squared, so your index 4 here, and minus mc squared, so what can you take? I'm not going to show you the binomial expansion, but if you make the binomial expansion, so if you binomially expand it, you will find out that actually mc squared equals 1 plus, because there are two minuses, plus half v squared over c squared, and minus mc squared. And now you can find that if you expand mc squared, you will basically effectively cancel these out, and you will get left with mc squared half v squared over c squared. And now you can cancel c squares, and you are left with a kinetic energy half mv squared. And this is a rough approximation of kinetic energy at low speed. So yes. And actually, I calculated using this equation, and for the minimum speed required for protons to produce that kind of thing, collision, was 2.121 multiplied by 10 to the power of 8, which is 70.7% of speed of light. And now we're going to talk about the pair. We're going to talk about annihilation and pair production. So it's important to realize that annihilation process is a process that happens when particle and antiparticle meet. So what actually happens if we have an electron and a positron, and if they move exactly to each other, so there is a head-on collision, what actually happens? They annihilate each other. So by emitting 2 gamma photons, and it's important to note that these gamma photons, in this case, to conserve the momentum, in this case, the the gamma photons have to be emitted perpendicular to the direction where the particle antiparticle came to, and 180 degrees to each other to conserve the momentum. And actually, if we go back to the beta decay, beta minus decay, so what actually happens to the nucleus? So this is electrons and stuff like that. So as we said, W minus boson is emitted, and then I'm sorry, we shall go to beta plus decay because positron is emitted there, I'm sorry. So beta plus decay. So positron, antiparticle of an electron is emitted with a neutrino. In this case, neutrino, not an antineutrino. And what actually happens? This is where nature has its annihilation process. So positron is emitted, it travels until it meets an electron, as I've described here, and 2 photons are emitted. So this is what actually happens in nature of the annihilation process. And we can actually describe this by using a equation, positron plus electron, we're resulting in 2 gamma photons, like something like that, yes. Yes, and now we're gonna move at more deep description of pair production involving nucleus. And I think this is quite interesting. So, okay, so you know fission process where we know that the mass of, for example, uranium has been converted into energy because the total mass of the reactant is greater than the total mass of the product. So, and pair production is completely opposite. So what actually happens in pair production? Energy is getting materialized, so it converts into the mass by using Einstein mass energy equivalence principle. Yeah, so we're going to explore that and involving nucleus. So we can actually summarize it by this kind of equation. So we're saying energy of a photon, it is resulting in electron, in this scenario electron, and plus positron, and plus something else that I will come back to that. So, and to picture it in the diagram like this. So what actually happens when we have a very energetic gamma photon with energy of so energy has to be greater than 2m, where m is the mass of an electron, c squared. Yeah, so what actually happens? A photon just passes by a medium, and now when it kind of sees a very quite heavy, heavy nucleus, what it actually does here at this point, the energy carried by the photon, which is equal to hf, is getting converted into mass in the form of electron, positron and electron. Yes, and positron and electron. And now you might really ask yourself, so this cannot happen without a nucleus. And now you might really ask yourself, why do we need nucleus? And the reason for that is the same. We need to conserve the momentum. And now I'm actually going to show to I'm not going to derive anything, but I'm going to show by just rearranging equations that actually photons have momentum. So if we have this equation, gamma mc squared, and we have momentum equation, which is gamma mv. If we rearrange these two equations by eliminating v, we will end up with an equation E squared equals pc squared plus m, where m is the rest mass, the only mass, c squared over squared, yes. So to satisfy, so if we want to take a photon as an example here, photons have mass of 0, and it doesn't matter that photon is traveling at speed of light. It still has a 0 mass, so the mass doesn't increase as the velocity increases. So what we can actually say is E equals pc. And from here, we can we can actually see that momentum is equal to energy divided by c. And from this we can say that P equals hfc, and we can link it back to the de Broglie wavelength, where momentum equals h over lambda, where lambda is a wavelength. So now we're linking back to this equation where we've studied in A-level physics about de Broglie wavelength. So now we can actually see that photons have momentum indeed, and now we're going to explore how can we actually prove the conservation of momentum here. Okay, to show the conservation of momentum here, we need to divide the collision. So this is before, and this is after. If we take after, so if we ignore the before bit, what we see is we just see that electrons are traveling. So electrons are traveling. Electron and positron is traveling in this kind of manner. What we need to do now is we need to take center of mass frame of reference, which just means we have to take velocity, we have to take speed and direction to move in, so that we as an observer, so this is us moving along with a speed that is equal to v1, and so we're going to choose the speed and the direction from which we as an observer see an electron and positron move in exactly opposite directions and with exactly same magnitudes of speed. And what we're actually getting, while traveling at velocity v1, we can actually say that the total momentum of this system is 0. Now, if we go back to, if we remember, we're still traveling with speed, with the speed v1, which is definitely less than c. If we go back to the before, we're traveling with v1, and now, relative to us, photon is still traveling at speed of light, which means photon, relative to us, photon still carries momentum. And what happens now is so it's kind of, the physics doesn't work here, because now we're seeing that there was a momentum relative to us in our center of mass frame of reference, and now there is no momentum. And this is where nucleus is tapping into the game. So what actually happens here, nucleus absorbs some of the momentum, so it gains some of the momentum in the direction, in the original direction of the photon. So nucleus is getting a recoil energy. So this is what the equation actually says. So the nucleus is very important here, and this is the reason why pair production cannot happen in a vacuum. And also, I've read a presentation from Professor at Oxford, and there was a sentence which is kind of hard to understand. If we have kinetic energy, half mv squared, and we have momentum, remember at low speeds, what we can actually say is that it says that energy, recoil, which is kind of equal to kinetic energy, is momentum squared divided by 2m. So yeah, so you can kind of get this equation from these equations. And what is this equation actually states is that for a constant momentum, as the mass of the nucleus increases, the energy of the recoil, so energy of the recoil decreases. Honestly, I've not really got my head around this. I only know that it is just a fact, but like I will get my understanding later. So yeah, and yeah, so now we are going to, okay, we are nearly the end. Now I'm going to explore the process called quantum fluctuations and as a description of such a phenomenon called Hawking radiation. So, another British theoretical physician called Stephen Hawking, he has proved that actually in large gravitational gradients that can be found near a black hole can actually cause a pair production process to occur, where in very abstract terms we can say that the gravitational energy of the black hole is getting converted into matter and escapes in the form of Hawking radiation. Therefore, the mass of the black hole is reducing. But we're going to try to explain it in terms of quantum fluctuations. So, what actually happens? And this is quite hard to explain. Okay. Quantum fluctuation is defined as a temporary change in the amount of energy in a point of space-time. And if we go back to the analogy where I have showed you a field, a quantum field. So if we go back to the analogy of quantum field, let's say we are in a pure vacuum where energy is zero. We have no energy, nothing in the vacuum, and the only thing in the vacuum there is mathematical quantum fields. Even though we have zero energy, the field is not still. It still has quantum disturbances, which means field is not really still and stationary. It's always like wibbles and wobbles, and each individual is called a quantum fluctuation. If we zoom in here, we can actually see that field is disturbed. And these quantum fluctuations, we need to go back to the Heisenberg's uncertainty principle, which states that the change in energy multiplied by change in time greater than reduced Planck's quantum, where h reduces h over 2 pi. You will see loads of different forms of this equation in the internet, but I've chosen this one. And so quantum fluctuation is governed by the principle of Heisenberg's uncertainty principle of energy and time. So what this equation actually states in its simplest terms, in this context, in simple analogy, this equation just says we can break the laws of physics, e.g. conservation of energy, as long as no one really notices. But in other words, from absolutely nothing, when energy is zero, we can get a quantum fluctuation where the energy, we will gain energy equals to E. So we gain energy equals to E for time duration which is equal to T that will satisfy this equation. As the energy that we can get from absolutely nothing increases, so as the uncertainty in the energy that we can get in the point of space and time from absolutely nothing increases, the time for which we can possess this energy decreases. And so what actually happens? From absolutely nothing, we can get energy. So we have borrowed energy from absolutely nothing due to quantum fluctuation, energy uncertainty principle. And what actually happens here, if we have a quite large uncertainty in gradient, this energy can get materialized into a particle, an antiparticle pair. So now we have gained particle and antiparticle pairs. This is virtual particles, and I'm going to explain briefly what virtual particles are. And what actually happens, now we've got two virtual particle and antiparticle pair from absolutely nothing. But what actually happens here is they annihilate, emitting gamma photons. So we end up with nothing again here. And this is fine because We started with nothing, from nothing we got something, and from something we got nothing again. And this whole process is happened in approximately 10 to the power minus 22, 23 seconds, depending on energy uncertainty. And this is what actually a pure vacuum is. If you take everything out of the box, absolutely everything, you'll get a billions or millions of billions virtual particles popping in and out of existence constantly. And now we're going to go back to the black hole, because if we have a black hole with singularity here, so it's singularity, and its event horizon here, remember that the escape velocity that you can calculate by equating half mv squared and gravitational potential energy here is greater than the speed of light, so you can't really escape the event horizon. So what actually happens here is when a quantum fluctuation happens near a black hole horizon, so event horizon, and we get this particle and antiparticle pair, one of the particles can fall into an event horizon, and if the other particle somehow manages to escape from the event horizon, so it wasn't in the event horizon in the first place, it was at the edge of it. So there is still a possibility for this particle to escape. We say that now they can't annihilate each other anymore because this is gone now. So what actually happens? We say at this stage, we say that we have gained energy, the universe has gained energy in the form of matter, and now the universe has to follow the rules. The universe says, no, we have to conserve the energy. No, this is completely like rubbish. And what actually happens? In this analogy, in a very simple explanation to that, when we say this particle has positive energy, remember this is just an analogy. This particle effectively becomes to have negative energy. And what actually happens? When black hole swallows a particle with a negative energy, the total rotational or total energy of the black hole is decreasing. So so it's decreasing, and the black hole is slowly it gets evaporated. And all black holes are getting evaporated, but you will not find, like, for example, in our Milky Way, there is a very large black hole, and you will not find it evaporating because it, for example, in our black hole, consumes far more mass than it actually emits. So we've done a little bit on that, and the last section is quark confinement that I was talking about. Okay. So now we're going to briefly describe what the quark confinement is. Okay, so back in the days, scientists, when they found out that actually subatomic particles are quarks, they kind of decided to separate constituent quark to study it individually. But spoiler, they have dramatically failed. And the reason for that is not because it's not like the book says, the strong nuclear force are indeed strong, and but the reason is lying in the examples that I'm going to show you. So what actually happens? Let's take, for example, a proton. So proton has a UUD, as we've said, and remember, they are strong nuclear forces that binding them together. So, what actually happens? When we supply energy to one of the constituent quarks, so when we kind of collide it with a photon, a very energetic electron, in this example, what actually happens is that a quark, this quark that has absorbed this energy, is actually the distance between the constituent quarks increases. So what actually happens? When we supply energy, the quark is getting elevated, so the quark is getting excited, and the distance between constituent quarks increases. And now, we have not really covered Coulomb's law, Coulomb's law, which state that the force experienced between charged particles is proportional to the magnitude of each charged particle divided by r squared. This basically originates from Newton's, because it's kind of similar with Newton's gravitational thing. And the interesting thing, it does not obey this, it does obey, but like strong nuclear force is kind of making it not visible in this scenario. Okay, so what actually happens? Strong nuclear force, which is mediated by gluons, is actually, as the distance between charged quarks increases, the strong nuclear force indeed increases as well. It's not remains same, because loads of people are saying it remains same, and loads of people are saying no, it's actually increases. But I'm gonna go with an increasing force. So what this system says, we need more energy. And when we say, okay, we're gonna supply even more energy, and now we are at the point where we are about to separate constituent quark. But this is the interesting thing. Let's imagine a guy standing. He's a physics god, okay? So he has laws that he always implements. So conservation of energy and conservation of charge. Basically, he's in charge of everything in here. And one of the laws that he has, if a system has an energy that is greater than 2mc squared, where m is the mass of a particle, in this case it's up quark, I will materialize it. So what actually happens here, we're saying to this guy, okay, we're supplying energy, we want a constituent quark, and then he's saying, okay, supply more energy. And what actually happens, when we continue to supply energy, what actually happens? We reach a point where energy supplied is greater than energy required to materialize energy in form of matter. In this case, it's up quark's mass. So we are ending up with our quark that we kind of tried to separate, and we end up with meson here, which in this example will consist of up quark and anti-up quark. So all energies that we have supplied to separate this quark has been converted into a particle-antiparticle pair. And this is quite sad, because within the next fraction of a second, this is going to annihilate because it's antiparticle and particle pair. And this guy effectively has tricked us. He said, oh yeah, supply more energy, but without telling us, he just converted all our supplied energy into mass without telling us. And this is why we can't really separate quarks. Also, quick fact, very interesting, is when the distance between, so in this scenario, when the distance between constituent quarks decreases, so they are very compactly packed within a proton, what actually happens? There is a phenomena called asymptotic freedom. So what actually happens? When they are very compactly packed, the strong nuclear force is actually decreasing. So they can actually move freely, like in this position, when they are actually completely packed together. Okay. So, yeah, this is the end, but I would like to add, do you remember when I was saying that the velocity mass doesn't increase because of velocity increases, and some of you found it very, very kind of weird, and it was kind of controversial. And this is actually what actually happens. And the main argument that you can here that, for example, if you say that mass doesn't really increases with the velocity, then you will, with your classical analogies, you have this law in your head, which is a gravitational law, gravitational force, and you will be tempted to explain why photons actually curve under the influence of gravity, and you will be tempted to use the analogy, you will be tempted to say, oh yeah, as the velocity increases to c, the mass of the photon increases, therefore the photon feels a force that points in this direction, therefore it curves. However, this is not true. The actual reason, we need to go to the Einstein's field equation, which was implemented in his not special relativity, standard, not how is it called? General theory of relativity. And he actually explains that the mass isn't like. He actually explains that the field has geometric properties, and that there is called stress energy tensor. And basically, what it says is that the gravity depends on the amount of energy and momentum. And as we have explored the photons having momentum, we can actually say this is a nice explanation to that phenomenon, not with an increasing mass as the velocity increases. So this is everything that I wanted to say. Thank you. No, I really appreciate it. Thank you for coming during summer. Yeah, really appreciated that. Thank you. Do you have any questions?
I'll let you guys go first.
Covered everything. It's far more detailed than I expected.
No questions?
I know. You probably have.
I've got questions. Yeah.
Okay, come on.
So you know when you've got two electrons coming close together when they repel?
Yes.
You said when you put your hand on the board, the light's being exchanged to push your hand back.
Yeah.
When I have this coffee cup right sitting on the table, experiencing a force.
Mm-hmm.
Where's that force coming from? Is it from that? Do you know?
So you mean the reaction force, where it's like?
Yeah, because the electrons from the surface of the plastic cup and the electrons from the surface of the table is the same as you putting your hand on the wall.
Yes.
So those photons, when the electrons come close together, are virtual.
Yes, because
they're not.
Yeah.
So like if you have a collision in space, for example, it doesn't glow. Right? They're virtual they're exchange particles. And actually only 10% of a reaction force like this comes from electron repulsion. 90% comes from the Pauli exclusion principle, which is that electrons don't like to be in the same state. And if you overcome the Pauli exclusion principle for electron degeneracy, it's a supernova, isn't it? That's how neutron stars are born.
Okay, so it's Pauli exclusion.
The Pauli exclusion principle.
I'm gonna make note of that.
Mm-hmm. But I mean, it was very comprehensive. There was a great deal in there. Things like having electron-positron emission. When they annihilate, the photons come out perpendicular, right? So that's how PET scans work. Right? PET scan they're tubes, aren't they? When you lie in there and you get scanned, it's a tube. Why is it a tube? Because the electrons come out, the photons come out perpendicular. So you can then locate where the tissue is in the body. That's why they're tubes.
That is actually very interesting.
Mm-hmm. So there's a lot of medical physics in there, like CAT scanning. Okay, that's done from photon interaction with the electron.
And I have a question to you.
Mm-hmm.
Like when I was doing a research, I got very confused about the term virtual particles, and I tried to explain. So as we have not really gone deeper into the nature of virtual particles, is it okay for me to say that virtual particles are indeed real particles that exist in a very small period, in a very short period of time?
Yeah, they pop in and out because they so it's related to borrowing energy from the vacuum, as you were saying. I haven't personally gone into virtual particles very deeply. I didn't choose that option at university, and whatever, it's not the one where my research is based. So I'm not too sure. But what you were saying with the vacuum energy, so if you take the wave function, which describes the dynamics of a particle entirely for the Schrödinger equation, if you take the wave function and the principal quantum number n, the lowest you can go is n equals 1. So the minimum energy is h bar omega, right? So you are, when the vacuum, even if you take everything out, it's still fizzing with energy, because as rightly you say, particles are popping in and out. As long as you borrow within the time limit of Heisenberg, you're fine. And the black hole stuff with the Hawking radiation, that is incredibly deep physics. I mean, there's a lot going on there, and you've explained it quite well. But actually, even if you do a bachelor's and a master's degree, you still will not cover that.
Okay.
That stuff is only covered in graduate research.
Yes.
Yeah. So basically, I mean, I went through the full system, and I never got to that.
Oh.
So there's a lot to be understood there.
Okay. And I've actually, what you said, so I've actually seen a diagram which is kind of something like this, which actually says n equals 1, or no, n equals 1 here, and it kind of tried to mathematically explain that below n1 we can only have virtual particles.
Yes,
but,
that is how it looks, and indeed the principal quantum number n equal 1 is the lowest state.
Yes. And any further question? I will actually read on Paul exclusion principle, because I've not really seen it before, but like
Yeah, so electrons have energy levels.
Yeah, like
right. Particles in the nucleus also have energy levels. You're not taught that at A level, but they do. So there's a degeneracy between electrons in the quantum states. So they don't like to be in the same states, and so if you push the electrons, for example, so if you have a plasma which the particles are unbound, so that which is protons, neutrons, electrons floating around in a hot plasma. If you squeeze the plasma, the electrons do not want to be next to each other. And if you squeeze it enough, the electrons are forced into the protons. Into the protons.
Yeah. So
And then you just form a huge ball of neutron matter.
Oh, that's why we have neutrons.
That's where a neutron star comes from. And that process, rightly so, as you say, through decay, the electroweak force emits neutrinos.
Yes.
And that neutrino emission is where supernova energy comes from.
Oh.
So only like 2% or whatever, like 1% of the energy in a supernova is light. In all of its neutrino emission.
Oh yeah, I forgot to mention. Neutrinos are the most abundant subatomic particles, but we can't really observe them. And Fermilab is actually
we can observe them. We can detect them.
But very, very hardly. So I believe they're doing something like Dune's experiment.
There's a few experiments there's a few places on Earth where we detect neutrino emission, because we can detect supernova before we see them, because the photons get clogged up with dust emission in the galaxies. They get clogged up with being bent in curved space-time and all sorts of things. But neutrinos don't. They just stream straight through the matter, basically. So we always see a neutrino spike maybe an hour or a day or two before we see the glow.
And then we can concentrate our telescopes.
So we can see the neutrino emission. And there are a few places on Earth, a big place in Canada with the Snow Plus experiment, seen that? So the neutrinos hit the like incredibly dense, I think it's water, and then the photons come out, and they use the tubes, the multiplier tubes to detect the neutrino emission. So that there are places,
Just a quick fact. Can I just ask you the last question of have you do you know and have you done have you ever come across the thing called cryogenic electron emission? Because this is what I cannot understand. Because what it actually says, it says that the cathode photon multiplier can emit an electron when the temperatures reach minus 70 Celsius, I think. And this is
I've not come across that.
I've tried to do a lecture on that, but I realized I will not able to do that because there are no explanation that I found. So I kind of switched to particle physics then.
No, I haven't come across that. But yeah, I mean, physics is wonderful, isn't it? And it all ties in together, right? Astrophysics, cosmology, particle physics. You know, the bridge between classical physics and quantum mechanics is thermodynamics. Quantum mechanics played out on large scales with millions and billions of particles, and it becomes classical physics, right?
Oh yeah.
This is classical. It's a classical force, isn't it? But as you go deeper into it, it becomes quantum, and so you're studying physics is great because you're the way it changes the way you view the world.
Yeah.
And indeed that as you go into different branches, you realise that it's actually all connected.
Yeah.
Yeah, well done.
Okay, thank you. Thank you for coming. I really appreciate that you have decided to come during summer. So, so it's a lecture now. It wasn't really a lecture. It was just a talk, really.
Yeah. Well, academic talks are typically between 10 minutes and an hour.
Oh.
So that's when you. But don't get me wrong. If you once a week at the university department, you'll have someone else come in from another university around the world to give a 1 hour talk on their research, because the idea is if you're doing your own research, you're very focused on it and you don't know what you don't know. So someone comes in to tell you what you don't know.
Oh, yes.
Yeah? So because there's so many different fields.
And the way Richard Feynman. So I think, in my opinion, I think my favorite topic. So I couldn't really understand how photons actually interact, and the interaction of photons goes deeper into the quantum electrodynamics, which I find quite interesting, but I don't have mathematical skills to kind of do a research on that.
Yeah, you'll cover QED if you do a master's degree in particle physics. Otherwise, it's not in the IOP curriculum. So I want to say all the good universities, but you shouldn't say that. All of the credible universities have their degrees accredited by the governing body. For physics, it's the Institute of Physics. For chemistry, it's the Royal Society of Chemistry, and so on. So these governing bodies outline what needs to be covered in that degree to become accredited.
Mm-hmm.
Quantum electrodynamics, quantum field theory, not in there, because it's advanced. So when you specialise, that's when you can go into that.
Okay.
Mm-hmm.
Yeah, thank you.
You're welcome.
So, yes. So, again,
Thanks,
thank you for coming. Really appreciate it. And this is over now.